Well, welcome everybody, and thank you so much for being here for Multithreading is the Answer. What is the question? A title which I wish I could take credit for, but my co-founder Barbara was the one that came up with that one. I'd like to take a second to set the stage and talk a little bit about where we're going to go, and as we explore what multithreading is, we're going to discuss some of the terminology that's involved in the practice of multithreading, talk about the problems you can solve with it and the problems that you shouldn't try to solve with it, which I think is a topic that is often overlooked when we discuss multithreading. And then I'm going to talk about how to review multithreaded code and share with you a better way for implementing a multithreaded design, a better abstraction for dealing with shared data in a multithreaded program. A lot of people will say, oh, multithreading, that's really complicated. Well, it is and it isn't, but part of the reason why it can be complicated is because it's difficult to talk about. And when Barbara and I were working on CppCon, which were the co-founders of the CppCon project, which is an open source cross-platform GUI library, we had a section where we needed to design some code that would be thread safe. And we weren't in control of how it would be called externally because we were in a library, so we don't know what the user will do. And we discovered that communicating about a multi-threaded piece of code was very challenging because, for one thing, the terminology can be confusing and people can disagree on what it means. And this is what happened in our case, was we had both done a great deal of concurrent programming. Mine had been more on the multi-threading side of the equation. Hers had been more on the multi-user database context of the equation. And in a multi-user environment, you deal with locks. And in a multi-threading environment, you deal with locks. And they are completely different, but we use the same word. So it's really important to get your terminology straight. So let's start there. No offense to anyone in the room named Bob, but the generic C++ programmer named Bob decides, I have something that I'd like to do, and I'd like to solve this problem using multithreading. There's your first mistake. If you choose multithreading as the solution before you decide that you must, you're making a mistake. Because you have more opportunities to shoot yourself in the foot. Because every multithreaded program can be reduced to one race condition which crashes. And you'll have a few memory leaks here and there, and you will have a high-profile customer find the bug you didn't, unless you're extraordinarily careful. However, it really helps to be working on a problem that is naturally solvable with multithreading. Because if you try to fit multithreading into an environment where it doesn't fit, you'll discover that it doesn't make sense, and you're working at cross purposes with the mechanism. So really, really ask yourself, is this a problem that I actually want to solve with threads? Is there some better way? And often the answer is yes. Now, in order to have a proper definition of all these terms, I'm going to start by defining multithreading itself, which, for our purposes, is the ability of a program to execute multiple instructions at the same time. Sometimes you might be sharing time on a single CPU with other threads, but the real complexity doesn't come in until you have multiple cores, all processing different stages of execution simultaneously and having effects on the state of the entire program. Sometimes people like to distinguish between concurrency and parallelism, because concurrency has a connotation that threads are working together to solve a particular problem. And parallelism is when the threads don't have to work together. If you can end up in that situation, it's great, because as we all know, working solo is simpler than working with someone else, although the solution may not be as good. There's also multitasking, which is really common in most operating systems. Any operating system worth its salt is a multitasking environment these days. And this is where you get into things like time slicing. I'm not going to go too much into that, but it's important to understand that multitasking is not multithreading. So let's have a quick little quiz. Who here thinks that threading makes a program faster? Anybody? Okay. Not necessarily. It can, but it doesn't always. Who wants to write a multi-threaded program so it can be really stable and reliable? I'm not seeing too many hands, and I'm seeing some snickers. I'm on the side of the snickers here. If you're smart enough, then multithreading will be easy. I'm going to bash that one right out of the gate. There is no sufficient level of intelligence that makes multithreading trivial. And threading might be useful for error recovery. Well, it turns out it's not. Threading can be more complex for error recovery because now you don't know what the state of something is if one thread has had a problem. But neither of the last two are true either. Multithreading is not hard and it is not easy. It is just a different discipline with its own set of constraints and requirements, and you need to be fluent in its language. A thread is nothing more than work that can run on one core at a time. A thread is part of a process. A process consists of multiple threads potentially, and each thread has its own stack. So in C++, all the state of the stack is local to your thread, and pretty much the entire global state of memory is shared. This is contrasted with a process, which is really a separate program. It's a separate memory space. It has its own copy of everything. And we deal with processes all the time in our build systems. Make runs a separate process to run the compiler and things like that. Threads in the same process share a lot of resources. A core, a lot of people have sort of an intuitive understanding of what a core is. The number of cores is really just the number of things that can be happening simultaneously in a processor to a reasonable approximation. And not all cores are equal in some environments. I'll be talking in this session about places where all the cores are equal, but there are cases where they're not. Things like NUMA and asymmetric multiprocessing. Those are more specialized topics. More cores does not mean faster. Our CI system has 6 cores because it's faster than the 8-core version of the same chip. Because when they added 2 extra cores, there was more heat generated, and so they had to slow down all of the cores to compensate. So it turns out the 6-core machine is actually capable of processing things much faster than the 8-core machine. The tricky bit, if there can be said to be only one tricky bit in multithreading, is dealing with resources correctly. A resource is, in generic terms, something which you don't want 2 threads to access simultaneously. And common things are a location in memory. We're fortunate in C++, since C++ 11, we have a well-defined memory model, so we can actually reason about the behavior of the memory in the process. File handles are not usually thread safe, and you may have objects that were written in your code that are not thread safe. You must make sure not to access them from multiple threads simultaneously. If you do, you have a race condition. And the exact definition of a race condition, as contained in C++, is in order for a race condition to occur, you have 2 accesses to the same location in memory, and at least one of them is a write. And it's important to understand that constraint because multiple reads are okay, but if there is a single write, all other simultaneous access is forbidden. And if you have 2 simultaneous accesses and one of them is a write, you will have undefined behavior. I cannot stress this enough. It's not a, you might get the wrong answer. It's not a, oh, well, if 2 threads increment the same value at the same time, it might increment it twice. No, it is undefined behavior, pure and simple. And there are architectures where you can get truly bizarre behavior if you have a race condition in your program. So it is of the utmost importance to prevent race conditions. It's not simply a nice property. As I mentioned, the stack belongs to a single thread. It's the area of memory we use for fixed size objects, and the heap is shared among all the threads. Fibers are another thing that we've used in various dialects of some programs. They're more of a lightweight thread. We have these in boost fiber. They're not that commonly used. They haven't been standardized into the language yet. And given the fact that coroutines are in the works, fibers may not make it too far into the standardization process at any point. I'm not quite sure about that. You'll also, in a few languages, run into what are called green threads for reasons that should be lost in the mists of time. But these are threads that are implemented in user space rather than by the operating system, and they have a lot of consequences when your environment uses green threads. You have to be very careful about how you interact, because if you block, you may be potentially blocking a large number of other threads simultaneously. This one is not that relevant to C++, but it's good to be aware of if you're interoperating with other systems in your environment, that they may have constraints on threading that we don't have to work under. So given all that, what do we actually want to do with multithreading now that we've defined some of the basic terms? When do you reach for multithreading in your toolbox? Well, the things I look for are if you have a task that can easily be split into independent steps. This is a nice property to have in any problem, but it also makes it tractable to work with in a multi-threaded implementation, because you might be able to split it up into independent processes that can run simultaneously. It really helps if each step has a very clear input and output. Or you know for a fact that you're extremely CPU bound and you're going to be using the entire CPU and you would like to use more than one CPU. It also can be very nice for a process that has a large read-only data set that never changes, but it has to be manipulated in various ways. This is a very natural place to use a multi-threaded solution. Or stream processing. It's quite common that if you can set up your program as sort of a data flow diagram, where you have data streaming in one side, passing through a set of transformations and streaming out the other side. It can be very natural to set up each of those paths along the stream graph, or each of those nodes along the stream graph, as a separate thread, and you can increase your performance considerably there. These are the problems where you look at them and you say, awesome, multi-threading will fit, I can solve this using threads, it will be great. Then there are the problems where you have to use multi-threading and you wish you didn't. And these are the ones that create interest and complexity in your code. If you have a task where the performance would just be completely unacceptable as a single thread, if you have to use more than one core, and you have a large data set and it has to be maintained synchronously between all of the tasks in your program, you need to consider multi-threading even if it's awkward. It's also very common that this shows up in places where you don't know the workload ahead of time, and you need an independent array of workers, all of which are capable of doing whichever task comes along at a given time. If you have a lot of resources, like you're an operating system, you have disk drives, you have network sockets, you have all sorts of things that you're managing concurrent access to, you must be multi-threaded. A non-multi-threaded operating system is completely useless at this point. And it's hard because you have a large number of resources to manage, and you can't allow contention, or you can't allow race conditions on the resources. You have to manage contention, and there's not a lot of tools for managing the complexity there. This is another case of if you have external clients making requests to you, or a web server, a database server, anything like that, you need to handle whatever comes your way as quickly as possible and get it out of the way for the next request. And you really probably ought to be looking at a multi-threaded solution. At a prior job that I had a real-life example of this. I was writing a streaming video server. There's a web server, and the prototype had really bad performance. It was unable to serve the traffic that we needed. And for production, we said, okay, well, let's make it as fast as possible. And I said, well, how fast is possible? Well, let me make this multi-threaded. No. Let me check if I can meet my performance goals without making this multi-threaded. And I simply optimized the code and refactored some of the internal data structures. And all of a sudden, I was able to saturate the network bandwidth that was available to us with 12% of one core. My job's done. I'm I/O bound. I will get no benefit out of multi-threading this code because I'm able to serve bits as fast as the network can take them away. So what difference does it make how many cores I'm running on to do this? Look for this. When you find this, be glad and avoid multi-threading if you can. What I'm going to be talking about here is sort of the sweet spot of the generic multi-threading environment. As I mentioned, there are some other areas that multi-threading is used, but this is sort of the desktop / mobile / cloud typical environment where we have some number of cores that you can count, possibly with taking your shoes off, and you have, they're all similar cores, the memory is fairly close together, we're not dealing with a supercomputer with the memory over in the other building. So if you have that situation, you may need additional complexity in your design. But in order to talk about multi-threading, I'd like to bring in an example. And the example is a restaurant kitchen. And we have a couple of chefs, and each chef is a thread. It can do work independently. And we have 2 knives. Each chef has their own knife. So they can work with the knife as needed and do whatever they want to do. And we say, okay, we have a big order came in. We need 50 fruit salads. So let's have each chef make 25 fruit salads. Now, as an aside, I really enjoy questions. I enjoy an interactive discussion as we go through this. So if anybody has questions as I'm going through this, please feel free to raise your hand. And the great thing about C++ and C++11 and the threading library that came in there is the code actually fits on a slide, because we have a simple enough threading system and the library is concise enough that this isn't fake code. This is real code on a slide. So I set up a thread. I name it chef1. That's the name of the variable that's going to represent this thread. And I just pass a lambda to the constructor of stdthread. I say, this is the work you will do when you start. And I'm going to count to 25 and make a fruit salad. And we do the same thing for chef2. And then at the end, we join both. And what that means is we're going to wait in the main thread until both chefs have finished their work. And then we know that they've completed, all the fruit salads are ready, and we can serve them. Any optimization that anybody can see here? Does this seem reasonable? Yeah, we seem to be in agreement on this one. I'm sorry? The chefs might work at different speeds. That is true. That is very true. Now, in this case, since they're doing exactly the same work, they'll probably be roughly the same speed, but it's a consideration that we need to take into account. In this case, it won't really affect anything. What it will mean is we'll still get the same result. But if one chef works at half the speed of the other, we're not really getting that much advantage from multi-threading, because the slower chef will stall everything. So that's a good point. Thank you for that. So now, let's make 50 apple pies. Now we need an oven. We have a resource. And remember, you can't use the same resource for multiple threads simultaneously, at least in the definition of resource I'm using in this presentation. So let's say, okay, let's have each chef make 50 apple pies. So we set up an oven. This is a global resource. And we set up a mutex to protect this oven. And each chef is going to 25 times make a pie, make the crust, put the apples in the pie, get it ready to go in the oven, then lock the mutex so that they know that they're the only accessor of the oven, bake the pie. Any problems with this design? Excellent observation. You could be preparing some more crust while you're waiting for the oven to be available. So this is an example of, this is a fairly simple example. We have one resource and 2 threads, and already we're getting into issues of, we're going to be blocking, waiting for this resource to become available. We have contention. Yes, sir? I'm sorry, I couldn't hear that. He has an oven which handles 2 pies simultaneously. That would certainly be an addition to this. Some resources can be used by some finite number of threads simultaneously. It's not common, but it does occur. You'd have a slightly different design and behavior here, but that's a good example. So let's make things even a little more complex. So let's take the idea that you could be making a crust while the pie is baking. And let's say instead of having both chefs do exactly the same work, let's have one chef make the pies and the other chef put them in the oven. Now, why would this be useful? Anybody care to guess as to why this would be helpful? Yes?
If they take about the same time, then that really minimizes the time that someone's waiting.
If they take about the same amount of time, then that minimizes the amount of time that somebody's sitting and waiting and doing nothing. That could absolutely be true. Another, yes? Excellent. You're getting at where I was going. Specialization. One chef might be better at making pies. The other chef might be better at baking them. That's a good point. I'll come back to that. Yes? It'll prevent deadlock because you only have one chef trying to put a pie in the oven. That's well stated, but in this example, since we only have one resource, and each chef locks the mutex and then uses the resource and unlocks the mutex, can we have a deadlock? And
But in your previous example, there could be deadlock. One chef might be preparing the pie, and he never knows like if the other person also.
there may be blocking. That's true. That's not a deadlock because it's a different situation. You'll still eventually make progress. You just may have to wait for the other chef to be done with the oven. Live lock, yes. You can get into a live lock situation if you have enough threads all working on this simultaneously. That is true. You can hit a live lock. There's no deadlock here. Like I said, terminology is exceedingly important in this area. Yes, that is, so thank you for bringing in a term that I actually didn't have in my slide deck. That's helpful. In this example, if one chef is fast enough at making pies that they're always acquiring the lock on the oven before the other chef can get their pie in the oven, then you have starvation. So one chef could end up completing their work much faster than the other one because they have better access to the shared resource. So that's a great example. In this case, since both of them are doing a fixed amount of work, you can't have starvation for an indefinite amount of time, but it can definitely make it so that one thread will complete much faster than the other. And that can be a property that you don't want in your system. So thank you for bringing that up. So getting back to the next idea of one chef prepares pies and the second chef is going to bake them. So in order to do this, we're going to need some way to move the pies from one chef to the other. So I'm going to, for sake of argument, say that we have a thread-safe queue. There are plenty of talks that you can go to about how to implement a thread-safe queue. I'm talking more abstractly about the way to plug together these multi-threading concepts into a working solution. So we have a conveyor belt that will take the pies from one chef to the other. So now our two chefs do completely different things. Chef 1 instantiates a pie, does everything that needs to be done to get it ready for the oven, and puts it on the conveyor belt. They give the pie away. And this is a key attribute to look for. If you can design your code so that you can give away ownership of something once you're done working on it, it is much, much easier to work with in a multi-threaded environment. Because whenever you have shared data, remember you can have a race condition. We don't want two processes, two threads accessing the same data at the same time. Well, if one thread creates something does all of the work on it it needs to do, and then gives it away to another thread, you can never have shared data. So in this case, we're using move to give away our ownership of this pie to the conveyor belt. Then the other chef just stands there waiting for a pie to come off the conveyor belt, pulls it off the belt, puts it in the oven, waits for the oven to finish, puts another pie in. Any questions on this phrasing of the problem and why this is potentially an improvement over the previous solution? Back there. I've moved the work of synchronizing the resource from the pie to the conveyor belt. Very well spotted, that's true. However, there is no way that I can allow, in my universe of this restaurant kitchen, there's no way I can allow two chefs to use the oven simultaneously. But there might be ways that I could allow them, one to put a pie on the conveyor belt and the other to take it off at the same time. There are certainly lockless queues where we can move data between threads without either thread having to wait. So I may have improved my solution by giving myself access to more tools to apply to this problem. Does that address your question? Thank you. Any other comments on that? I'm sorry? You might make too many pies for the conveyor belt to hold, yes. So that's the opposite of starvation, where one thread gets ahead of the process, and you might have to have some way to throttle the first thread or allow an arbitrary size buffer so that it can grow to consume this work backlog that the second thread has incurred. Yes?
The data sharing is still here, it's just hidden inside the queue, which brings up a great point about multithreading in general. If you can make it somebody else's problem, do it. You got a thread safe queue from somebody, maybe a log-free queue, good for you, you don't see data sharing anymore.
Yes, that's very well stated, and in general, the best strategy for writing a safe multi-threaded data structure is get it from someone else, because they've probably broken it in at least the ways they could discover. So you have a better chance. Yes, if you acquire a known safe, thread-safe queue from someone else, then by all means, find a place to use it in your program to reduce your larger problem to using somebody else's solution to an already solved problem. It's very helpful. So thank you for that. So, can we hit a deadlock in this case? Not if our thread-safe queue is implemented correctly, because it's the only place where both threads are operating on simultaneously. Can we make this more optimal? Well, we've talked about several ways in which it could be better or worse than the preceding design, depending upon your constraints, what the costs are for the various resources, what the costs are for synchronization. Are there any race conditions? No, this design is correct. Again, assuming the code you got from somebody else to implement a thread-safe queue works properly. You're done. Now let's deal with the complexity of a real commercial kitchen. And this is what you have. You have orders coming in all the time for random things. You have resources. You have I'm sorry. Let me get slightly ahead of myself. Let's deal with a slightly less complex commercial kitchen first, where we have two things that we need to do. This is more of a catering setup. So we need 25 fruit salads and 25 chicken salads. Which of these strategies sounds like a better option? We could have each chef make a fruit salad, clean up his workstation, make a chicken salad, clean up his workstation again, and do that 25 times. Does that sound like a good use of time? What about one chef makes 25 fruit salads, the other chef makes 25 chicken salads? Does that sound advantageous? I get a thumbs up. Would you care to venture a reason why this would be a good solution? We don't spend any time cleaning the kitchen. Well, maybe once at the end, but we save a lot of time during the middle. Absolutely. It's a good solution. Very, very good. It's a good solution if they take about the same time. If a fruit salad is much faster to make than a chicken salad, it may not be the best solution. It might be, depending upon what you're optimizing for. If what you want to do is to get the most work done in a particular amount of time, it might be a good solution, even though the chicken salads will take longer to come out. It can be reasonable. Or we can do what we don't want to have to do in a multi-threaded program and contain some shared state, where both chefs start out working on one thing and then they switch over to the other once enough has been made. This way, if one chef works slightly faster than the other at the beginning, we'll still end up with the right number and we'll have the lowest latency to having all 50 salads available. Does that seem reasonable? Again, there's no right answer here. These are trade-offs. It depends on what you're optimizing for in your particular case. Now, let's talk about a real kitchen. We have a lot of resources. They all do different things. They're all unique. They can't be substituted for one another. And anybody can just walk up to the counter and order whatever they would like at any time. How do you optimize for this? You don't know the workload. You don't know how long your chefs are going to take. You don't know what's going to be busy when you go to try to fill an order. What do? This is the real multi-threading problem. This is not the simple one that you like to solve with multi-threading. This is the one you have when you have no other choice. So let's start working through this and develop this example and see how we can apply the tools in C++11 to this so that we can make some sense of it. And then in the next section, I'll show you some additional tools that we can build on top of the language to reduce the complexity of this solution and make it more tractable. So first, let's set up our resources. So we have an oven, and we have now two, because we need the Viking oven for baking pies, and we need the brick oven for baking pizza. And the brick oven will be used for both the pizza and the garlic knots. So now I have a resource that's shared among multiple different things that I might be working on as well. And I have an ice cream maker. And we declare mutexes for each one of these so that we can manage the resource contention and enforce that only one chef will use them at a given time. I have a bunch of classes. I have a class hierarchy of the various foods that people might want to eat. And what I really want to do is eat some food. That's the ultimate goal of this exercise. Everything else is just machinery. Always identify the output in a multi-threaded program and try to work back from there to see what machinery you need underlying the solution. So in order to eat something, I need to consume food. So I'm going to consume it by R-value reference because once I'm done with it, it's no longer edible. So I'm just going to print a message that says I was successfully served my food. And I'm going to set up a couple of tickets. So we're going to use the future and promise system in C++11. And I look at the future and promise system as the equivalent of the ticket you get when you order a sandwich at a sandwich shop. It gets split into two halves. One half goes to the chef. It tells the chef what work I would like you to do. This is the sandwich I want. I get the other half. Later on, when the work is done, we can pair them up. I get my result. I get my food. So this is the future promise system, and this is the value of doing this rather than some other mechanism for getting data back from another thread. And you'll note that these are working with unique pointers. The T inside the future and promise are unique pointers. Unique pointer is the best feature that they added to the threading library in C++11. Because unique pointer is a fantastic tool for preventing shared data. And if you can, prevent shared data. So I've got a couple of patrons, and they're going to come up and they're going to order random things in a random order and then eat them. And note that when we call eat, we're passing it, we're using the ticket that we got back, we're using the future, and we're calling get. And when we call get, the patron is going to sit at their table and wait until that particular food is available, and then it will become available, it will show up in your local thread, and you can eat it. Or if the chef gave up and there was a problem like the oven caught on fire and it couldn't finish making the food, when you sit to try to eat the food, what you eat instead will be an exception. And you can catch that exception and do whatever you'd like with it at that point. But this is a very useful tool because it means that, remember, I was mentioning, multithreading does not always make your program more reliable. Well, at least we have a way to manage the unreliability because we will get an exception if the other thread fails to complete its promise. We're going to set up an order. That is a thing that can be passed around so that we know what to work on. And we set up a flag that says, is the restaurant still open? Because we need to know when to send the chefs home. And since we can't send the chefs home, we need to set a flag in a place that they can see it when they're done working on an order and leave and go home of their own accord. And the chefs actually become very simple. We just take another order off the queue and we work on it. This looks fairly straightforward. Well, what does an order actually do? Well, an order is nothing more than a wrapper for work that is to be done. This is also sometimes called a work unit in a threading system. So when I want to order some pizza, I'm going to set up a future promise pair. I'm going to set up this chef ticket that I have. And then I'm going to encode in the order all the work that I want done by the chef. So I want the chef to go make a new pizza, add the sauce, add the cheese, go acquire the lock on the brick oven, bake the pizza, and then give the pizza back to me. This whole setup returns immediately because I'm not actually asking the work to be done. I'm just saying this is the work I would like to have done later by someone else. So this order pizza method returns immediately and returns the future that says, at some point in the future, when the chef gets around to it and all of this work is done, you will have a pizza in front of you. That's our promise. If you're in C++14, you can capture by move of the promise, which means you don't need a shared pointer to do this. C++ 11 lambdas didn't quite have all this functionality available. So, what are the consequences of this? Well, okay, we have a single queue, so we might have contention on the queue of orders. So what could we do about that? Well, if we split it up into multiple queues, one for each chef, then it can potentially be much faster because each chef has to only check one queue. But then what if the chef is sitting there waiting for work and there's stuff to do in another chef's queue? So now you go look at the other chef's queue and steal the work from them. This is work stealing, and it's a very common attribute in thread pools. So in order to implement correctly and efficiently a work queue, there's a lot of complexity that goes into this. Again, try to get one. Don't write it yourself. There's a lot of tricks to doing this properly. A chef really shouldn't be sitting there waiting for a pizza to bake because we're wasting an entire thread just sitting there doing nothing, staring at an oven, waiting for it to be done. And if you go back a little bit, this locking is kind of arbitrary. There's a thing called a brick oven mutex, and there's a thing called a brick oven. And you have to lock one before you use the other. There ought to be a better way. So think on that. Now, before I move on to the second part, I'll take a few minutes to talk about some miscellaneous advice for how threads should be pulled together in a program and what to look for when you're writing multi-threading code. This is a really common mistake. If you have too many threads runnable at a given time, it can be very slow in the operating system. This is usually not what you want. When people start working with threads, they think, okay, I have 500 things I want to do, so I'll start a thread for each one. And that's not what you want. What you want is some number of threads roughly proportional to the number of cores on your system. Depending upon your design, it might be 1-to-1 or it might be 2-to-1. I've seen some cases where that's useful, where you have one set of threads that's doing a very complex CPU-bound operation, and you have another set of threads that handles all the I/O-bound operations. And each of those should be represented on a single core, so you need 2 threads for each core in the total system. So you really want to aim for 1 or 2 active threads per core. More is not really a great thing. We want to really move the blocking calls out to ancillary threads. So you really want to see if you can partition your work into CPU-bound and I/O-bound components, and then split this apart into separate pools of threads. This can really improve your performance in areas like network servers that are doing a lot of processing, but also doing a lot of I/O. Too much shared data. I know I've said this a few times. I can't repeat it enough times. If you have shared data, you have the potential for a race condition. The less potential you have for a race condition, the more correct your code will be. So really try hard when formulating your problem to reduce the set of shared data that you have to work with. Reduce the size of the shared data that you have to work with. Maybe even compute some values individually in each thread rather than fetching it from a common location. It will often be an improvement. Reduce the number of threads that need shared data if you do have some need for sharing. It's really the same idea as encapsulation that we've all been doing as object-oriented programmers for many years, for those of you that actually use the object-oriented part of C++. Trying to compartmentalize your system so that the number of parts of the system that have access to shared data simultaneously is the minimum feasible. And this should be your main design goal. It is often more efficient to reduce the amount of shared data and duplicate work. And if you do have shared data and you can make it read-only, huge win. Read-only data is better for caching. It's also better for reasoning about the behavior of the system. Oftentimes you can set up a system where you create a large shared data structure initially, but then once the process is up and running, the individual threads only need read access to the shared data structure. If you can do this, do so. Mark it const. Make it very explicit that this data is read-only, and you will know that once you've reached that point in your program where the data is no longer written to, your code is race condition free. And we aim for an environment where you can look at a piece of code and say, I know, a priori, that piece of code is race condition free because I can reason about its behavior and I know what it's doing when it accesses shared data. If you don't have that property, then you have to work through each example separately. And I'll talk more about that in the second half. So as I just said, the property that we're aiming for is as little shared writable data as possible. That is the #1 concern that should drive your data structure design in your program. Now, when you're reviewing multi-threaded code, there are many things to look for, and there are better ways to arrange your code, your data, and your access to the data. And stick around for part 2. If any of this interests you, or if you're interested in any of the other projects that we've worked on, you can definitely come find us on YouTube. Please do subscribe to our YouTube channel. We have content coming out every 2 weeks about C++, multi-threading, CppCon, and the various other projects that we work on. It's of general interest to the C++ community, even if you're not using our libraries. Some of the things that we've worked on include CppCon, as I mentioned. It's a library, a cross-platform GUI library. We've also refactored out of that the CS signal library, which is a thread-aware signal delivery mechanism This is actually a large part of what drove this talk, was developing the CS Signal library and encountering some of the challenges in working with a library that needs to be thread safe in this context. There's also the CS String library, which is our standalone Unicode aware, both UTF-8 and UTF-16 support string library, and libguarded, which will be the subject of the second half of this talk. And some additional programs that we've worked on. Kitchen Sink is a demo application if you're interested in CopperSpice and how it works. Diamond, which is a programmer's editor written in CopperSpice, very lightweight cross-platform programmer's editor. And DoxyPress, which is a documentation generator that uses Clang on the front end for correct documentation of C++ source code. Our information is available all online, and you can contact us through email. We welcome comments and questions. And now I'll turn the floor open to questions here in the room. Comments, observations? All right. Well, in the next session, I'll be going over the entire design of libguarded, which is a system for managing access to shared data in a multi-threaded environment without losing your mind and without invoking race conditions. And I hope you stick around for that, because I'll be going much deeper into this example and showing you how to reduce the complexity of what we've developed in our multi-threading vocabulary at this point. Thank you.